Hello class, today we are going to talk about tangents of circles. Now before we get into that, we do want to talk about some definitions. So first off, what's a circle? Circle is the set of all points that are a set distance from a given point, called the center. So this is circle P. And we name a circle like this. This is the abbreviation. Make sure you put the little dot in the middle of the circle there. Otherwise, it would just look like OP. All right, so you put the dot in the middle of it that way. It's circle P. All right, and all of these points are the exact same distance away from the center, which is P. All right, circle is named by its center. Now, the radius. This is a segment from the center to a point on the circle. So segment AP is the radius. The radius is also used to describe the distance from the circle to the center. All right, it's either the distance from the circle to the center, or it is the segment from the circle to the center. Either way is referred to as the radius of the circle. All right. Here's one you may not have heard before. This is a chord. A chord is a segment that has endpoints on the circle. So segment BC is a chord. One end of the segment's on the circle, the other end of the segment is on the circle. That's a chord. All right. A diameter is a special kind of chord that passes through the center of the circle. So segment BD is a diameter. This is still a chord of the circle. All right. Then you have secant. A secant is a line that passes all the way through the circle. So line BC. Notice it does not stop at B or C. It keeps going. All right. So this is something that is going to intersect the circle twice and keep going all the way through the circle. And the last one we have here is tangent. Tangent is a line that touches a circle at only one point. All right, so line EF is tangent to circle P at point D. D is the only place where it actually touches the circle. Point D is also referred to as the point of tangency. Okay, it is the point at which the line is tangent to the circle. This has nothing at all to do with the trigonometry tangent, okay? Totally different. Same word, totally different meaning, all right? All right, so lines are tangent, and tangents are what we're mostly going to be talking about today, but also circles can be tangent to each other. For example, if I take these two circles and I stick them right here, they're only touching at one point. If I could put them in here. Again, only touching at one point, so these are tangent circles, all right? Tangent circles. Another thing we're going to look at here, you can have common tangents, something that is tangent to both circles. For example, these red lines here. These are common tangents. These are referred to as common internal tangents because they are in between the two circles. And you also have common external tangents, like these. The green lines are external tangents because they are not in between the circles. All right? So here you have these two circles have four common tangents, two internal tangents, two external tangents. You could also have circles like that. You only have three common tangents, with only one of them being internal. These circles here, these are tangent circles. So that line in the middle, that internal tangent, is tangent to both circles, and the circles are also tangent to each other. Here we have some intersecting circles, and so they only have external tangents, because you can't draw a line in between them without going through the circles twice. Here we only have one external tangent, again no internal tangent, and again these circles are tangent to each other. And then we have this where we have no common tangents, and these are called concentric circles. They have the same center. Concentric means centered together, so they have the same center. All right, so let's look at some stuff to do with tangent segments and lines. First, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at the point of tangency. All right, so what this means is my line is tangent to circle C because it intersects the radius right there at the point of tangency, and it is perpendicular. So if I move it in, well, it's still perpendicular, but you can see it's not tangent. It's now a secant because it's intersecting at two places, right? It has to be it has to intersect the radius at that point of tangency right there on the circle. also it has to be a right angle. If it's not a right angle, if we turn it, we see, again, it becomes a secant. It's intersecting at two places, not just one. All right. So tangent lines are perpendicular to the radius. And so next thing we're going to talk about, tangent segments from a common external point are congruent. So since these two segments are tangent to the circle and they have a common endpoint right here, they're congruent to each other. That's what that says. All right. So now let's take a look at this. Let's do some examples, see what we can use this for. So here we go. We want to know, is segment CB tangent to circle A? So here's segment CB right there. We have a radius, 5. We know that A is the center of the circle because that's the name of the circle. So we know that 5 is the radius. This segment here is 9, and BC has a length of 13. Well, if segment CB is tangent, that means that this has to be a right angle, which means we have a right triangle. And if we have a right triangle, then we can test this with Pythagorean theorem, right? So Pythagorean theorem, a squared plus b squared equals c squared. Let's test this out. So what is a? Well, a is 5, b is 13. How long is c? Well, c is not 9. 9 is just from point C to the circle. We also need this right here. Well, since this is a radius, just like that is, then it's also going to be 5. All right. So we have is 5 squared plus 13 squared is maybe equal to 9 plus 5 squared. So 9 plus 5, so 14 squared. And so that doesn't work. We're sticking our calculator, 5 squared plus 13 squared is 194. And 9 squared plus 5 squared, so 14 squared is 196. So we see Pythagorean theorem did not work, and so what that means is that this is not a right triangle, and so segment CB is not tangent to circle A. Looks tangent, but the numbers say it's not. It's off by a little bit. All right? Because again, if it's tangent, it has to be a right angle. So here we go. This time we're telling us that segment BC is tangent to circle A at point B, and we want to find the radius of circle A. So again, if it's a tangent, that means that this is a right angle, so we have a right triangle, and so we can use Pythagorean theorem. A squared plus b squared equals c squared. Again, remember C is opposite the right angle. So C for this is segment AC. Well, we have some issues here. So A is R, that's our radius, what we're looking for. B is 24. C, though, how long is my hypotenuse? It is not 18. It is 18 plus R. It's that whole length, right? So when we do this, remember, when you square 18 plus R, you've got to FOIL it. This is 18 plus R times 18 plus R. So you FOIL that together. All right, as you end up with this. So R squared is just R squared, we don't know. 24 squared is 576, and 18 plus R squared is 324 plus 36R plus R squared. Again, you got to FOIL this together. Well, we want to solve this. We want to get all of our R's to one side, so let's move this R squared from this side to that side. So we subtract R squared from both sides, and look at that. The R squareds are both going to cancel out. And so we end up with this, which is a lot nicer looking because we don't have quadratics anymore. So again, we're going to subtract the 324 from both sides so we can get R by itself. Divide by 36R, just by 36, the R stays there. And we end up with R is 7. So we have a radius of 7, all right? Because the tangent is perpendicular to the radius. All right, last example. Circle C is inscribed in polygon WXYZ. What inscribed means, it means that all the sides of the polygon are tangent to the circle. So these are all tangents. We want to find the perimeter of WXYZ. Well, perimeter, that means, of course, that we're going to add up all the sides. The problem is that we don't know all the sides. I know that this segment here is 5, but I don't know how big this piece is. I'll go ahead and tell you that it is not 5. All right? Just because they are tangent doesn't mean it bisects. What it does mean is that since this side, WX and WZ, intersect at W, it means these two tangent segments are congruent to each other. So if this is 5, this is also 5. All right? So down here, since this side is 2, this segment right there is 2, that means this segment is also 2. Okay? Question, how big is this? Well, it's not 5. It's going to be the same as this one here, which I don't know. It is not 11. 11 is the entire side XY, right? Well, hey, that's 3, right? Which means this is 3. These two, because they have a common endpoint for these tangent segments. So if this is 3, the whole thing is 11. 11 minus 3, and so this piece is 8, which means that this piece is also 8. Now I have all my sides, I can add them up. 5 plus 5 plus 2 plus 2 plus 3 plus 3 plus 8 plus 8. Like that. I'm not using the 11, notice, okay, because 11 is the whole thing. I could use the 11 instead of using this 8 and that 3, that's fine. This is a little bit easier for me because it's got 5 and 5, 2 and 2, 3 and 3, 8 and 8. Easier to make sure I got everything in there. And you just add that up, and the perimeter is 36. So, just to recap, common endpoints on a tangent means that the two tangent segments will be congruent to each other. And if a segment is tangent to a circle, it must be perpendicular to the radius. All right? Has to be perpendicular to the radius at that point of tangency, or it is not tangent to the circle. Hopefully you found that useful. I will see you in the next video.